Alright, welcome to lesson 5.10. Here we're going to continue writing exponential functions to model continuous growth and decay, and then we're going to use technology to solve some exponential equations. Let's get started. Alright, so we're going to pick up where we left off with the bank deposit question, the interest question. And what I want you to do right now is pause and go back over the question, make sure that you understand the function for bank A and bank B, and use those to think about bank C again, and try to write an equation that represents the amount in bank C. And you might remember some things from class, and that's totally fine. Go ahead and implement those as well, and then we'll try and pick up where we left off. All right, let's go quickly over banks A and B, and so we can move on to bank C. We, of course, have here a situation where your interest is 1.5% per year. That's the rate at which you're gaining interest. And bank A is going to compute that interest, is going to add that interest on at the end of the year. So it's just going to, at the very end of the year, it's going to say, okay, I'm going to take 1.5% of whatever you have, and I'm going to add it on. And so you get the equation A of t is equal to 200 times 1.015 t. Multiplying by 1.015 will increase your amount by 1.5%. And that's going to occur every time t increases by 1 because the exponent is t. So after 4 years, you have $212.27. So let's take a look at bank B now. Bank B uses the same annual interest rate, meaning that you're gaining interest at a rate of 1.5% per year, but it's actually going to stop and give you your interest according to that same rate every 6 months. So if you think about it, when you take a rate of 1.5% per year, that's the same as saying half of that percent every 6 months, which is exactly why when we're computing the growth factor, we take 0.015 and divide it by 2. In other words, we're actually every 6 months going to be getting 0.75%. So we're going to go ahead and take 1 plus 0.015 over 2, which is 1.0075, exactly what we expect. And since we're multiplying by this base twice every year, we need an exponent of 2t, so that every time t increases by 1, we will actually be compounding that interest twice because it happens every 6 months. So computing B of 4, we get $212.32. So we can see we're making a little bit more money, and that should make sense because when you compound that interest twice, you're gaining a little bit of interest the first time. So the next time you take the interest, there's actually a little more in your bank account, and that little bit more gains some interest as well. So you end up with, slightly more than you would have in situation A. All right, let's move on to C here. This is the interesting one. So the difference between B and C is that C is actually going to compound your interest continuously, meaning at every instant during the year in equal percentages. So just like bank B did, it's going to take the annual interest rate and it's going to say, okay, since it's 1.5% each year, we're going to break that up into smaller components. The difference is that bank C is breaking it up into every instant. Well, how many instants do you have? If you tried to count them all, you'd be here forever because there are infinitely many. So what we need to do is break up this 1.5% into infinitely small pieces so that we can add on those infinitely small percentages every single instant, which seems to be a pretty complex, convoluted type of deal. But let's just try and write it out as best we can. So we're going to take the annual interest rate, 0.015, and we're going to divide it by the number of instants, just like we did in bank B, except here there are infinitely many. Now, we don't have a very great way of representing infinitely many, so we're going to come up with one that makes sense. I'm going to put the infinity symbol in quotation marks here, because it's not actually correct mathematical notation to divide something by infinity. And when you see this, what we're thinking about is a number n that is getting closer and closer to infinity. We're used to this notation here. So we're thinking about a number n that is approaching infinity. Okay. So we have this idea here. We have no idea what this actually is going to be, but we understand what we're trying to do. Now we want to think about the exponent. we're going to have some base, which when we multiply 200 by this base is going to add on that really small percentage, right? This number that we can't quite get a hold of. And we're going to do that infinitely many times each year. So we want to have an exponent that every time t increases by 1 will result in us multiplying by this, you guessed it, infinitely many times. So we're going to do the same thing here. We're going to have this infinity, and I put it in quotation marks again, times t. And again, what I'm thinking about is this number n that is approaching infinity. In other words, it represents the number of instants that occur during a year. Okay, so at this point, what on earth do we have going on here? How are we going to make sense of this situation? It's actually going to be surprisingly easy. Before we can do this, there are a couple things. First, you need to have a calculator, and if you don't have a calculator with you, you can go ahead and go to wolframalpha.com so that you can go ahead and take part in the trial that we're going to do. We also need to take this 0.015 and we need to actually get it outside of the base. The reason we need to do this is we're looking at a specific situation where we have a given interest rate, but we want to come up with something that's going to be applicable anytime we're compounding interest continuously. We want to know what the base is going to be. So we're going to try and do something to get 0.015 out of the base. Now, the way that we're going to do that is not something that someone came up with overnight. It was a lot of trial and error that took this method and actually put it into use here. So don't think that you should be able to understand it right off the bat. You might want to take some time and rewind and go over again and come by and ask questions to make sure you understand. What we're going to do is we're going to introduce a new variable that will allow us to move this 0.015 out of our base. And the new variable that I'm going to introduce is the variable x. Now, here's how I'm going to introduce it. I'm going to say that x is equal to, and when I'm referring to this infinity thing here, I'm going to refer to the number n, which we know is approaching infinity. So I'm going to say that x is n divided by 0.015. Okay. Now, what does this mean? Well, we want to put x into our expression here. Notice that what we have going on with our 0.015 is that we have 0.015 over n. Now, x is n over 0.015. So if we want to replace this expression with something that involves x, we need to actually take the reciprocal of both sides. So we have 0.015 over this infinity thing here. So this means that 1 over x, if we take the reciprocal of both sides, is 0.015 over n. Okay, great. That is going to allow us to rewrite this thing inside our base. And that's great. That rational expression is going to change, and now it's just going to be 1 over x. This also, however, allows us to rewrite this infinity thing up here. And the reason it allows us to do that is that x is equal to n over 0.015, and that means that x times 0.015 is equal to n by multiplying by 0.015 on both sides. All right, so that piece is going to allow us to rewrite that part there. Okay, so let's go ahead and rewrite our equation here. We have 200 times 1 plus the 0.015 over n. That is the same as writing 1 over x. So I have 1 over x. Now we move into the exponent. Now we want to rewrite the exponent in terms of our new variable x as well, and since we have this n that's approaching infinity here times t, well, n is the same as 0.015 times x. And I'm going to write it as x times 0.015 times t, our variable t. Okay, so we're getting closer, but still, what on earth is going on here? We have this variable x, and what's happening to x? What is x? Well, x, we said, is n divided by 0.015. And n was this number that represented the number of instants. It was approaching infinity. So what happens when you take a number that's approaching infinity and divide it by a very small number? Well, you're going to get x, and that's going to be a huge number. It's going to be approaching infinity as well. So when we see x, we're thinking about a number, I'm going to put it in quotation marks again, that is approaching infinity. Okay. Well, what the hell do we do with that then? Well, before we can sort of get a handle on this, let's try and get all of the things that are approaching infinity sort of in one place. And what I mean by that is let's take this rest of our exponent, and using the property of exponents, we can actually rewrite this as the base raised to the x power, and then all of that raised to the power of 0.015 times t, so that we'll have all the x parts sort of isolated together. And I've written that right here. So now what we're stuck with is this situation where we have 1 plus 1 over x, and x is approaching infinity, it's basically infinity, raised to the x power, which is again this number that's approaching infinity. Well, what do you think this is? You might think it's infinity, you might think it just doesn't exist, your calculator will explode. You know, what the heck, how would you even try to get a handle on this? Well, we can do a little test. Since we know x is getting really big, it's approaching infinity, let's see what happens when we plug bigger and bigger numbers in for x, and we compute 1 plus 1 over x to the x power. So let's start with 100, and we'll work our way up. So get out your calculator. You're going to start with 100, so you'll enter parentheses 1 plus 1 over 100, close parentheses, and then raise that to the 100th power. Do that now. As long as you entered it correctly, what you're going to get is 2.7048, so on and so forth. So we'll write 2.704, and then we'll just stop there. We'll round to 3 decimal places. All right, so now try 1,000. 1 plus 1 over 1,000 to the 1,000th power. If you did that correctly, you're going to get 2.716. Interesting. All right, let's plug in a really, really big number. Go for 1,000,000. If you did so correctly, you'll see that you get 2.718. And what you should be noticing is that even though we're plugging in really, really large x values, the number that we get from our computation is pretty similar. So try making it even bigger, add another 0 or 2, and you'll notice that you still get the same first 4 digits, 2.718, and maybe even the 5th digit and the 6th digit stayed the same as well. That's because when we are computing this, as x gets bigger and bigger, it's getting closer and closer to this value, 2.718, and it goes on and on and on forever and ever. This is called Euler's constant, and it's exactly the value of the base that we're looking for. We can approximate it using the first 4 digits, 2.718, even though it goes on forever and ever. And we can use this approximation for our function. So what we have is now the equation C of t is equal to 200 times 2.718, all raised to the 0.015 times t power. And using that equation, we can compute C of 4. So go ahead and do that now. Now, if you did everything correctly, you'll get $212.37, a little bit more than if you only compounded the interest twice a year, and still more than if you compounded only once at the end of each year, which of course makes perfect sense. This is great because things in life don't just grow after a certain time period. Just think about your own height, right? You didn't wake up on your 10th birthday and all of a sudden shoot up an inch or 2 from the height you were on your 9th birthday. You're actually growing over the course of every instant between your 9th and 10th birthdays. And so now we have a way of modeling things that are growing at a continuous rate. Notice here that our base was this 2.178, so on and so forth. Our exponent consisted of the rate of growth, this 1.5% per year as a decimal, times the time, t, which was the number of years, and that corresponds to the growth rate, right? So your growth rate is percent per year, and you're multiplying it by the number of years. We still have the initial value out front. The only thing that we've discovered is the base that allows us to replicate continuous growth. And we'll see it can actually help us replicate continuous decay as well. Let's go ahead and take a look at the formal statement of continuous growth or decay. All right, so continuous growth or decay. When a quantity A is growing or decaying continuously, we can model the amount of the quantity using the following equation. The amount A is equal to A sub 0 times E raised to the R times T power. Now, R is the growth or decay rate per time period T. So in the previous example, the growth rate was 1.5% per year. T is years. So it would be 0.015 times T, where R is written in decimal form, obviously. And think about if we're decaying, the rate would be negative. Just remember, when we were writing exponential decay functions, we have 1 minus R. Okay? So we can see that negative there needs to be included. And A sub 0 is the initial amount. Really important to note that E is not a variable. This is Euler's number, which is 2.71828, so on and so forth. It goes on forever, just like pi does. And the way that E is actually computed is just how we did it in the previous problem. It was looking at what happens to that 1 over 1 plus x to the x power as x gets really, really big. That is exactly what Euler's number is. And we can approximate it with 2.718. Your calculator actually has a button for this number E, and so when you're computing things in your calculator, you can actually just put in the little letter E, and it will approximate it for you. All right, I hope that wasn't too much. If you need to go back and rewatch any of it, please do so that tomorrow we can go ahead and answer some questions that deal with continuous growth or decay.